hardware accelerator for implementing the Winograd-based minimal filtering algorithm for improving convolution. Convolution neural networks are one of the major components in the modern ML domain, as they are primarily used in any kind of image-related models, as they can reduce the spatial data into relevant patterns and features, and these are further passed on to fully connected layers to extract important information. One of the major drawbacks with the convolution neural networks is their extensive computation, even with the less number of weight values. This increases with the number of feature maps and number of kernels and the channels of the input data. In order to overcome this, many methods have been proposed throughout the years, and they have been leveraged in both hardware as well as software domains. And today we are going to discuss the major filtering aspect, and we are going to implement that in a hardware accelerator so that uh, the computation is much faster than the corresponding software implementation. Let's go through the Winograd's minimal filtering algorithm. Basically, a normal convolution application of a 3 by 3 kernel applied onto a input space will result in a 9 multiplications. Winograd's algorithm essentially converts those 9 multiplications into 4 multiplications and offsets most of the operations into additions. This is the primary formula that is used in Winograd's minimal filtering algorithm. There is a transform is applied to both the feature map and the kernel map. Finally, this is multiplied, pre-multiplied and post-multiplied by a particular matrix, which transposes them back into the original domain, thereby giving us the required computation. These are fixed matrices, so they can be implemented as lookup tables or as normal additions. When we compare the complexity, as you can easily see from currently from our observation and later in our code, there will be a 2.25 times improvement in our computational operation, as multiplication is one of the heavier computational operations that we are trying to reduce. For the hardware system architecture, we are primarily focused our design on the Zinc MPSoC architecture, as it provides a processing unit as well as a programmable layer, and we were planning to implement the acceleration part on the programmable layer and our main inference model on the processor core. This will help us to efficiently do the inference and as well as accelerate the uh, most computationally intensive part in an intelligent manner. Our primarily our programmable layer has the following components. There is an input buffer, there is a transformation unit, there is an element wise multiplication, and then there is an inverse transformation. This is the system level block diagram. Here we can see that this is the system on chip, and this is the connection layer, intermediate connection there that is used. All the communications are through an AXI master and slave communication. The master communication will access the inbuilt RAM of the DRAM of the SoC, and the control wires are connected. Control wires are accessed by the processor to initialize as well as control the various actions of the computation module. The full layout is added in the appendix. For implementation of this particular architecture, we have used the Vitis HLS software module, as implementing this in a completely in a Verilog domain will result in a less than optimal solution and will not allow us to focus more on the algorithmic as well as other design aspects. By using the Vitis HLS tool, we can effectively model the data flow and focus more on the algorithm, and also guarantee a synthesis of a model which is optimal in its results. So there are some uh, compiler directives associated with the HLS, which defines the various parameters related to our hardware. So these are the few of the pragmas that we must keep in mind. So first is the interface pragmas. This is similar to that of the declaration of the inputs and outputs in a Verilog module. So a interface pragma defines a input or output interface, and we can define the size and depth of the data in the interface. So primarily we have three interfaces, one to three master interfaces, one to pass the input filter, one to pass the input image map and one for the output. There is also another interface which is a slave interface which is used to control the module, which is given as bundle is equal to control, which essentially uh, implements all the necessary controlling operations in the module itself. This is a small block diagram indicating the various parts. These are the three major master inputs and this is the slave output. This is the computational module. Then there is array partitioning. Array partitioning essentially helps us to access various elements of the array concurrently. In a normal array, in a RAM, the arrays are stored in a serial manner. So we can only access one element at a time. By partitioning the arrays, we are essentially storing them in different registers, so they can be accessed in parallel and processes can be completed in parallel. And since we only have kernels of fixed sizes, this won't grow in an unpredictable manner. We have a fixed size. This the trade-off is that we need more hardware area to store a larger kernel, but it speeds up processing by allowing us to parallelly access all the elements. Loop directives are another set of pragmas that we must keep in mind. The unroll and the loop trip count essentially helps only in the uh, prediction of the clock cycle. However, the unroll operation helps us to parallelize our operations. Essentially, if we have a loop with a fixed number of operations, the unroll operation essentially tries to find ways so that they can be run in parallel. This is a summary of the optimization that I have explained currently. Let us take a look at the code. This is the main module that we have defined. These are the local buffers that we have defined. Since accessing the main memory for storing the intermediate values will result in greater latency as well as energy, we have defined a set of local buffers which will be implemented as block RAMs, either as block RAMs or as flip-flops inside the hardware, which will result in more hardware utilization. However, it will greatly improve the throughput as well as the latency of our application. So these are the interfaces that we have defined. A depth of 9 indicates a 3 by 3 kernel in this particular 3 by 3 kernel. Depth of 4 indicates the 4 by 4 input feature map. And the output indicates a 2 by 2 matrix. Here we are partitioning the various variables. So we are partitioning in the second dimension of G, and of the GG matrix also we are partitioning in the second dimension completely. Complete partitioning indicates that each of the elements in that dimension will be uh, allocated into a separate register, so that the elements of those dimensions can be accessed in parallel. And for each of the intermediate variables, we have implemented at least one level of register level partitioning so as to improve parallelism. So first stage is reading of our feature map and the kernel. So what we are provided with is an address for the G and the D. Using that, we have to first load the uh, values into a local buffer. Once we have loaded that, we can compute the various transformations. This is the GG transfers. This essentially takes place in one singular step, as these are non-interdependent variables. As you can see, this will only happen with 0th I, this will only happen with first I, second I, and third I. So the row-wise operations will take place in parallel. This will greatly improve our speeds. And we can also see that only addition and subtraction operations as well as shift operation is taking place here. So there isn't much hardware use in this one. Most of the operations are single cycle or one or two cycles will be taking place. Further, G transpose multiplication with G transpose is also a similar process with great parallelization and only addition and subtraction of shift operations. Similar kind of transformation is applied to the feature map as well. This is those operations. Only we can also see here also that only addition, subtraction, or similar kind of operations are only being taking place. One of the heavier operations that happens here primarily is the element-wise multiplication which takes place. Here we can see that a 16 number of operations have to be taken place, and these operations will be taking place in parallel, as U and V are completely partitioned, and the only real uh, drawback is the multiplication, which has to take place for each of the four rows and columns, essentially resulting in 16 multiplications. But This will essentially give us the output for a 4 by 4 feature map. For a corresponding normal convolution operation, this will result in 36 operations, essentially 9 operations, and 4 of such will result in 36 operations. But here only 16 operations will take place. 16 multiplication operations will take place. Finally, we have to transform back using some addition operations, and we will pass them to the output memory locations. There is a test bench written in plain C code. We have defined a normal convolution function which will do element-wise multiplication for a stride of 2 for individual states, and we can use that to compare the actual output with the output calculated by our Winograd module. Essentially, this is our kernel, which is flattened out into a 9 element array, and this is our feature map flattened out into a 16 element array. This is the location to store the output of the Winograd that we have implemented, and this is the location where we store the direct convolution output. We can run this using the C simulation in the Vitus HLS software. When we run this, you can see that it will take some time. You can see that the actual output is matching with the output with the accelerator. This helps us in verifying the correctness of the output. We can change some values and see whether this will occur in the same manner. So and further, we can run the synthesis so as to find the hardware requirements and the resource utilization of this particular implementation. All the Verilog code is automatically generated by the HLS. That is the primary objective, so that we can all the pipelining and such uh, important important and efficiency related matters can be handled by the software itself. Here we can see the timing estimates and utilization. We had a target timing estimate of 10 nanosecond in worst case, but we got an estimate of 7.3, which is better than the target. There is an uncertainty of 2.7 nanosecond. Here we can see the latency of each of the operations. You can see that read operations are the ones that are taking the most number of interval, and pipeline compute will only take a fraction of that. In total, 4,500, almost 4,500 lookup tables, 6,000 flip-flops, 21 DSPs, and 2 block solvers. These are the primary in terms of percentage values. That's very less because this module has a lot of lookup tables. Yeah. So from the synthesis, we can see that this produces a very efficient output, and we can use this in accelerating our inference models.